Welcome to Freeslate's webinar on automated solutions to accelerate drug development. This webinar is part of our ongoing series on this topic. My name is Justin Fisher and I'm the Head of Product Management at Freeslate, and I'll be your host today. Today you'll hear a presentation on some formulation work we performed using the Freeslate Biologics formulation system. We're pleased to have Dr. Russell Burge from Freeslate joining us today. Russell earned a Bachelor of Science degree in biochemistry from Arizona State University in Tempe. He obtained a Ph.D. in molecular biology and biochemistry from the Scripps Research Institute in La Jolla, California. After graduation, Russell received a postdoctoral training at the University of Colorado in Boulder. During postdoctoral training, Russell worked on biophysical characterization of RNA and DNA aptamers relevant to the biopharmaceutical industry. Russell then joined KBI Biopharma as a scientist, where he worked on more than a dozen biopharmaceutical development projects. Currently, Russell is an application scientist at Freeslate. Before we begin, let me invite you to submit any questions using the Q&A menu on the left of your screen. In the Q&A window, you can type in your question and press the Submit button. Any questions that we do not get to will be answered privately in a follow-up email message. The title of Russell's presentation today is Applying Automation to Accelerate Formulation Development.
All right, so thank you very much, Justin. Now I'll begin the webinar. Today I want to talk a little bit about, give you an introduction to Freeslate as a company and what we do. Specifically, Freeslate is a company that has integrated automation solutions for drug development for both large molecule and small molecule. And specifically, we start with making our own proprietary automation platforms. So in this figure at the top, you can see what we call our Core Module 3 robotics system. This includes elements of liquid handling, solid dispensing, viscous liquid dispensing, as well as analytical capabilities that are proprietary technologies for the Freeslate. And as you can see in the bottom right-hand corner, we have what we call our LIA software. That's the Lab Execution and Analysis software. In essence, this software is designed to handle the challenge of high-throughput data management. So specifically, this software suite allows the scientists to design their experiments, analyze all the experiments, and create reports with all of this large amount of data that can be generated by these automation platforms. And as you can see on the left side, we also work together with our customers and potential customers to understand what is it that they do and what are the different bottlenecks and challenges that they need to surmount. And we use our automation to help them meet these challenges. So today, specifically, I'll be talking about two case studies that were performed here at Freeslate. And in the first case study, this is a case study of where we used plate-based high-throughput formulation screening. So specifically, this is more geared towards early-stage development, where there's lower amounts of material, possibly lower concentrations of material, and it's more focused on rapid screening and robustness studies of different candidate formulations. And in case study 2, we're looking at perhaps a later stage study and a larger volume study where we're looking at vial-based stability studies. In this particular case, the intention was to make a hybrid study where not only are we putting our vials on stability, but we're also using the high throughput technology to provide us information that would also normally be gleaned by high throughput screening, such as buffer and pH screens. We also incorporate elements of force degradation to help us understand the performances of the formulations in the final container closure. And clearly there's some relation to short-term accelerated stability studies with this particular case study. And so the intention there is to demonstrate how these automated systems can help solve these challenges that development scientists and the analytical laboratories that support them may have. So specifically, these demonstrations are to show the increase in the efficiency of the collection, the storage, the analysis, the presentation of the data. So specifically, in these particular cases, these are workflows that are designed for certain customers of ours and certain segments of the market. However, the intention here is to show the different unit operations and the different capabilities of the systems, and the intention there is to show that these systems are configurable and are also flexible, and it's not necessary that we're trying to push any kind of high throughput solution on any laboratory, but rather we're offering all these capabilities that can work together with the current activities of formulation scientists. So highlighted in this presentation will also be our automated formulation preparation and analytical sample preparation. And we'll also be talking about how the Freeslate proprietary analytics are used to automate previously laborious and manual methods. So to go into a little bit more detail about our LIA software, you can see on the right side there are basically 3 different software programs as part of this software suite. And they map quite well to this overarching idea here on the left of the typical practice in the laboratory, from going from the experimental design, the execution, the actual analysis, and then the reporting of that data. And as I hinted to earlier, when we have these high throughput studies, not only can the design and the execution be a challenge, but also in the end the reporting can be a challenge as well. So we solve this by first we have what we call our Library Studio software, which is an array-based experimental design software suite, which allows the experimenter to tell basically given commands that will then be brought to the automation systems, and the automation systems will interpret those via Automation Studio. And at that point, all of those commands that were given to the library design in Library Studio will then be translated into code for the robot, and the instrument control will then go from there. And it will not only control the Freeslate analytics and liquid handling and solid handling capabilities, but it will also interact and control third-party analytics such as UPLCs, HPLCs, DLS, UV, and the like. And then in the end, we have our PolyView software program, which allows for the rapid visualization of the raw data and process data that are created from these large pipelines of experimental analyses. And I'll go into a little bit more detail now about how LIA looks in the real world. So again, we have our design, our execute, our analyze, and our report sort of workflow here. And we can see in the beginning, we basically have our scientists will maybe be at the robot or their desk, or possibly even logging in from another site, and they'll create a library design, which I'll show in a moment. And that library design will then go to an Oracle database, which can then be which can communicate with an application server. So then the scientist basically is the center of all this. They can continue planning and querying and reporting from their desk or from multiple locations. And the point there is that they just need to be interacting with the application server. And also an important point here is to note that really this entire scheme can be performed by just one scientist. Let's see here. So then now we have our automation systems that are also connected to the application server, and from either remotely logging in or actually being there at the robot, the scientist can bring in the commands from the design and implement those designs and have the system do its liquid handling, viscous liquid handling, possibly solid dispensing, and all the analytics. And those analytics are basically also connected to the application server, whether they be third-party analytics or Freeslate proprietary analytics. And those are all basically communicating with the application server. So again, just like you would run the Freeslate robotic system, we would use the LIA software to run DLS or UPLC, HPLC, UV, and other analyses depending on our customers. We have a multitude of other analytical devices that our software will actually run the analyses, and then it will automatically take the data that is generated by those systems and bring it back to the application server and save it into the database. So you can clearly see here that it kind of looks like one big system using one software suite. And all of the data then, no matter where these systems are, these different analytical devices, all of that data is saved into one database in the end. And this simplifies the reporting with PolyView, because our PolyView software then will query that database, and it's up to the scientists and their managers then to create different types of reports, and I'll go into more detail about that. And the idea there is that there aren't these separate databases or computers. It's all sort of saved in one convenient location. Okay, so we have our experimental design in LIA. So this is a slide showing our software called Library Studio. And it is relatively small, but what we can see here is that overall it's a recipe-oriented approach. So you can define experiments, you can define different parameters and different ways of mixing things and different procedures and sequences. And so, for instance, in the top left-hand panel, it's a little bit hard to read because it's small, but there are different chemicals and combinations of chemicals, but there are also different processing parameters such as mixing and pausing and heating, different delays, and there can also be different analytical commands such as measure DLS or measure UV, etc. And it goes into this bottom panel here where it says maps. Again, it's small, but basically there's this logical sequence of different actions that will say add a certain amount of material, such and such, then perhaps run some sort of processing parameter. Once the processing parameter is done, then for instance there could be aliquots out for HPLC and whatnot. So you can get an idea of the sort of logic and the sort of simplicity of the overall language here that's necessary to tell the system what to do. And this provides a relatively easy template for people to make these designs, and it's also then there's the ability for the managers to quickly look through and review this information. And then at the top here, on the top right, you can see there are some pie charts, and this is just one of the ways you can look at the data. But basically, this is showing an example of there are 6 vials in one rack, and there's 1 vial in another, and these different components just tell you the different makeup in a graphical way. So the intention here is to show the overarching library design and to see that not only is it a sequence of actions and different chemicals, but you can also use the software to create different ratios and formulas, and the software then can get information about your stocks solutions and your intended final amounts, and it will actually calculate those final amounts for you, and then you can see that information prior to processing your procedures. So in the end, we noticed that there is a lot of information here, and a lot of our customers have this sort of data management challenge where if you have high throughput science, then you have high throughput data, and you have to make sense of it all. So in this particular case, we're looking at some data from a formulation study, and we used PolyView to help us understand what happened in the course of the analysis of these different formulations. So for instance, on the left side, you can see there are these 10 different formulations. They have a library ID which is assigned to them and is not, this is not editable, and it is fully auditable. And the idea here is that over time, that material was aliquoted out and analyzed via several different analytical steps. So there was HPLC, gel electrophoresis, DLS, etc. But all of those different analytical methods can be traced back to these parent vials, if you will. And so the idea is that our data management solution will basically allow the scientists to rapidly map back all of the different analytical results back to the original vials, and it makes it very easy to create what we call a dashboard view here, where scientists and their managers could sit down and quickly look at the report that's generated and understand, are things meeting specifications, or perhaps are they even able to tell which formulations are performing better than others. So this software allows for those types of decision-making processes. We also connect to specialized informatics such as JMP and Spotfire. And in the bottom right here is just to show how PolyView can create three-dimensional bar charts and other graphs and tables to help understand the large amount of data that can be produced by these systems. So clearly there are a lot of challenges to formulation development, and specifically at Freeslate we've tried to address those challenges and bottlenecks using our automation systems and our software. So one important point here is that at Freeslate we are trying to make an integrated hardware and software system all together that enables one scientist to perform an entire study, or largely perform an entire study, even if it has multiple analytical techniques that go along with the procedure and the study. So the way we can do this is we can increase the throughput for the methods and procedures that are going to be performed compared to manual performance. And the way we do that is we automate previously tedious and strenuous procedures compared to things that are oftentimes manual, such as visual inspection or pH, for instance. And that allows then the scientists to focus more on making scientific decisions based on the data, to move forward, to think about different studies and bring the formulation science to a conclusion, or certainly iterate to a much better formulation. We've also worked in low material consumption as one of our specifications. So in these two case studies we'll see that there are different levels of material consumption, but the intention is to limit the amount of material that's used and still create a large amount of information from which the scientists can draw upon. So as I mentioned before, having all of the data automatically saved into one database with the ability to link those results back to the original vials rapidly is a huge advantage from the sense that you don't have to worry about trying to collate data or find where the data is on multiple databases. It's all in one spot, and it's all relatively easy to create these reports. And then we have also, in addition to increasing the efficiency, we also think that there are some significant improvements that the automation can provide. So for instance, the Freeslate automated systems can alleviate subjective interpretation of assay results, such as color, particles, and turbidity, for instance, because our analytical devices will actually use calibration curves based on standards. And there's no need for secondary container labeling, and because of that, there's less chances of mislabeled or misplaced samples because of how the systems are actually working with the different vials and samples. There's a level of reproducibility with these systems that's extremely high, and that's due to the fact that prior to any study, all of the different capabilities of the system, including liquid handling, solid dosing, viscous liquid dispensing, all of that can be calibrated. And because everything is, all of the data and everything that's ever done with the samples is saved automatically into one database that is where the raw data is not editable, that allows for high data integrity. If the scientists need to go back and reprocess the data, then a new experiment, if you will, is generated, and that raw data is then reprocessed and saved as a new set of data. So the Biologics formulation system that's developed by Freeslate was used to perform both of these case studies. So this is a relatively large system. As you can see, it's encompassed in a HEPA enclosure. So it's a plexiglass enclosure with two HEPA filters on the top, which provide a level of laminar flow of purified air. And so we basically can create an aseptic environment inside this workspace. And inside, on this deck, there are three Freeslate robots. There's on the right side, there's what we call our formulation and analytical sample prep and analysis robot. So this can perform formulation, manipulation, and preparation, as well as creating analytical plates with different samples for later analysis. But it can also provide information such as pH measurements, viscosity measurements, and it can also do visual inspection on the deck. In the center we have our carousel, and this allows for additional storage space for extra samples or possibly other consumables that are necessary for the study, and it also allows for any kind of materials that are in a 96-well SLAS format to be transferred from the right robot over to the left robot. And the left robot is what we call our analytical CM3 robot. And basically this is a robot that allows for additional third-party analytics and other capabilities to be accessed by our robotic system and be fully automated. So in this case we have a Wyatt DLS, we have an Ixion centrifuge, we have an M2 Spectramax, etc. And the intention there is so that you can create this entire workflow with as minimal amount of manual intervention is necessary. So you can see all the different integrated capabilities. The system has quite a few capabilities in a very small amount of space, and not only can it perform different analytical tests, but it can also perform processing steps such as vortexing and heating and cooling. And some of these methods can also be used then for stressing the samples or possibly storing the samples. And we also have potential third-party analytics. For this particular set of studies, we used HPLC, which was off the deck, but was still being run by the same software that we run this whole system with, and it was connected to the same database. So there are definitely some challenges that we're trying to address with the system. So one thing is formulators are interested in looking at many different compositions over the development timeline for a biologic formulation. And so what we're looking for is to increase the number of formulations without necessarily having to increase the number of scientists or increase the amount of time necessary. So what we're doing here is trying to enable the formulation scientists to look at more conditions of buffer, both type, or actually type, strength, and the pHs, excipient types, and the levels of those excipients, and also possibly the API concentration. So the way we are able then to use all this information is once those formulations are created, we need to expose those formulations to stresses so that we can differentiate between the different robustness of the formulations. Now, in the beginning, in early stage formulation, we may have some challenges with material availability. And so that's where case study 1 comes into play, where it uses a very small amount of material, low concentration. And then we also have some challenges with liquid compounding versus rigorous buffer exchange. So in case study 2, actually in both case studies, liquid compounding was used to create the formulations, but currently Freeslate does have a system that can perform fully automated rigorous buffer exchange, but we'll save that information for another webinar. So case study 1, as I mentioned before, is a plate-based formulation screening program or procedure, and basically it starts with just 4 formulations that the scientists have to create, or should I say 4 buffers that they have to create. And our automation, our liquid handling will draw from these different solutions and mix them at different ratios, and then you get a diversity of different pHs all at the same concentration. So now we can take material from these vials that's on the deck of the automated system, and we can dilute those with Wi-Fi, and we can create water for injection, and we can create a diversity of different ionic strengths. And then by adding API and excipients, now we have 96 different formulations with varied ionic strengths of the buffers and variations on the different excipients. And then we can take this plate, which is now in a 96 well UV plate that's compatible with DLS, and we can provide some initial information by looking at the absorption at 350 nanometers, which can give us some information about the turbidity of the system of the different formulations. And then the next thing we do is we take this plate and we move it to our DLS system, which is part of the integrated workflow or part of the workspace. And inside the DLS, we collect information about the particles in each of the formulations, but we also use the DLS system to ramp the temperature from room temperature to 68 degrees with a few degrees a minute gradient. And in the end, we get more information about the turbidity by measuring the A350 after the temperature ramp. And then the intention here is to rapidly screen out those formulations that are performing poorly. And the way the scientists know they're performing poorly is because the turbidities will start to increase rapidly in those formulations that are performing badly. And then once we know which formulations are more robust, we can cherry pick those, if you will. We can select for only those formulations that are performing well, and then go on to do further analyses such as HPLC with SEC. So then as we can see here, that we're using PolyView to take a look at some of this data. So on the left side of this panel, we see the 96 well format of the different formulations, and we can see that the different levels of the A350. So initially, before the temperature ramp, we can see that the turbidities are very, very low for all of the formulations. And then upon heating, after the heat ramp is finished, we can see that for many of the formulations, the turbidity increases significantly. And that increase in turbidity suggests poor performance. Then we can also look at, we have this sort of multivariable plot here on the top right where we have the radius of the different particles in solution as a function of the temperature ramp. And we actually have multiple dimensions here. So there's a color gradient. So low pH is basically blue, and neutral pH is red, and anything in between is sort of a color ramp. But we also have sizes and shapes of the data protectors to show the different ionic strengths and the different components of the formulations. So this is just an example of how you can get a lot of information onto one plot, and it will help the scientists make decisions to drive forward with the formulation development. And then once the DLS data and the A350 data is understood and reported and perhaps even discussed, there can be some limited number of SEC runs that can be performed to support those formulations that appear to be performing the best. And then with that information, those candidates can be those candidate formulations can then be moved forward in the formulation development space. So in the end, this case study 1 is designed to show how we can make a diverse set of formulations rapidly from a small set of stocks. And as I mentioned before, with the HEPA filters and the ability to mostly sterilize the system, we can have a aseptic environment with which to work with. And we also have we can examine the behavior and the stability of a large set of formulation variants. So it doesn't necessarily have to be just one 96 well plate because of the processivity of these automation systems. Many 96 well plates could be screened in theory in the same day. So the data, as we've seen before, can be used to narrow down for further testing, and that can make things more efficient as far as how many samples need to be tested in the end. And as we can see, the PolyView enables these customized reports that can enable informed decision making and sound scientific decision making. For case study 2, this is a little bit more of a broader application. So this could be from early stage all the way to later stage formulation development. It's vial-based formulation screening, and the intention here is to solve some of the, or address some of the challenges that formulation scientists and their analytical support groups face. So in this particular case, we're showing how we're able to perform the formulation of these, we can perform the formulation preparation using liquid compounding of sterile solutions in the aseptic environment. And this includes viscous solutions such as high concentration API that needs to be handled into the different vials. One thing we wanted to show here is how in certain cases, stability studies normally are in a relatively small number of formulations. Once you start to get into the 2R, 2 ml vial formats, the intention here is to show how perhaps the automation can enable many more formulations to be screened across multiple stress conditions. Again, we're showing how our data management is able to analyze, collate, reprocess all this data that's being generated from these multitude of sources. And then we're going to show how Freeslate has automated previously laborious methods, specifically visual inspection, viscosity measurements, and pH measurements. And the intention is to have a system that can be highly reproducible over the course of a study or between studies. So the overall procedure of this particular study is shown in the center with these rectangles. And on the left are the different automation steps, and on the right are the different manual operation steps. So in the beginning, the analyst has to set up their stocks, their vials, and their consumables on the deck of the system. But once that's all set up, then the liquid handling capabilities, both air displacement and positive displacement, will be used along with the cooled and vortexer modules to prepare the formulations and stock solutions. So most of that time is actually unattended labor that is performed by the automation only. And then once those vials are finished, and in this particular case we capped them and stoppered them and crimped them so that we could take a certain set of those vials and put them on stability. And for the T0 samples, we performed then the on-deck and analytical tests on those sealed vials. So specifically, that's our visual inspection, which I'll show in a moment. And then after visual inspection, we uncap the vials, and then we use the liquid handling capabilities to aliquot and or dilute the material for analytical tests onto different plates in different vials. And again, the scientists and the analysts have to set up the plates and the vials on the system. And then once the material is aliquoted and diluted, the system is able then to perform certain analyses on the deck, and other analyses can be performed off of the deck depending on where the analytical devices are. In some cases, the robotics can move those plates to the analytical destinations. In other cases, analysts or scientists can choose to manually move those plates and vial racks to the instruments. And then we can use the automation, the heating and cooling and vortexing modules of the automation to enable some stressing conditions to be tested. And the intention there is to stress the samples in the vials, in these 2R vials, and then start the process again with the performance of the on-deck and off-deck analytics. And so the workflow is sort of, it starts with formulation preparation. And just to show you very quickly how we did this, we made 2 plates with 24 formulations each. That's a total of 48 formulations with 5 different buffer systems, pHs ranging from 4.5 to 7, 4 different excipient conditions, and we use a protein concentration at 10 mg per ml. And in the end, I'll show the table that shows all 48 formulations. But one thing you can see here is if you wanted to see the information that shows the different formulations that have been made, you can just simply double-click on the design for that particular vial, and you can see from the BSA stock how much material was added, etc., all the way down to a total volume. So then the overall workflow or the procedure that we used is once the formulation was completed and the vials were stoppered and sealed, we used our vision station. So here you can see our robotic vial gripper is putting one of these 2R vials into a vision station where color, turbidity, and visible particles are all measured. And then we can uncap and unseal those vials, and we can aliquot out material that's undiluted and perform viscosity and pH on the same set of vials. And then from there, we can draw more material from that first plate if the material is precious, so we're using less overall material. And we can use that plate to create many other analytical plates. In this particular case study, we used one plate for UV and DLS, and we had another plate for SEC, and there was also another plate for reverse phase HPLC. But as you can see, the emphasis here is for this first pH and viscosity plate to only have a couple hundred microliters of material removed from those initial vials. So this enables then the low sample consumption specification that we're looking for. So not only were analytical devices used in this study, but we also used the Freeslate systems to stress the samples. So on the left side we can see we have our vision station, our viscometer, and 4-probe pH meter. All of these are proprietary technologies of Freeslate, which are designed for to meet the challenges of the formulation scientists. And we also had the third-party instruments. So these were on the actual workspace, the UV Vis and the DLS. And then in another lab was the HPLC, but it was connected via the application server and the Oracle database. And it was also, and all of that material, all of these different steps were run by the LIA software. In addition to that, you can see the specifics of the stresses that were that the 2 ml vials were exposed to. And in only one case did we have to perform those off deck because we were doing freeze thaw from -80 to room temperature, which is lower than our current chillers can go down to. So to show the results, so this table is intended to be sort of dense because it's showing just a subset of the different information that was captured from the first day of testing for the T0 time point. So in this case, one scientist was able to perform all the T0 testing in a single day. In the sense of, well, in the case of the HPLC, those HPLC runs were initiated on the first day, but were not completed. But all of the other analytical capabilities were performed in the same day. DLS is not shown in this table just for clarity. And so the intention here is to show how we have about 6 to 9 minutes per formulation to perform our automated analyses, and that includes the aliquoting and dilution with the liquid handling. And so if we look at, if we start to look at some of the data in a graphical format, so in this case we use PolyView to export out to Excel to show the flexibility of our software to then create a multitude of different types of data presentation. So in this slide we have the visible particles and the counts as a function of their formulation and stress condition. So initially we can see there are very few particles in any particular vial, and after heating we start to see an increase in the number of visible particles in some of the vials. Agitation and freeze thaw don't seem to increase the visible particles in the same way as heating does. We also noticed that there were color increases that were observed in formulations after heating. So we can see here on the far right, after heat, we see formulations 2 and 4 and 26, which are all low pH formulations, are starting to have a significant increase in the brown-yellow tint. And 37 through 48, which are all histidine buffers, those all have, again, a significant increase in the color. So we also looked at the turbidity as a function of formulation and stress condition. And here we can see that in the beginning there's relatively low turbidities across all the formulations. Perhaps freeze thaw even increases the turbidity somewhat, but upon heating we see marked increases in the turbidity across many of the formulations. So here we can start to see some differences in the performance of the formulations. So the DLS is giving us a little bit more information about the particles that are forming upon the different stress conditions. So we can see that in what we're seeing here is that the formation of particles is correlated to low pH conditions. So those are those formulations from 1 to 4 and in the low 20s. Those are all low pH formulations which appear to have a correlation with particle formation. We also then have our reverse phase data, which shows clearly that initially the protein is at high concentration and high purity, is what I mean, high purity. And throughout all formulations and all stress conditions, we see that the protein maintains its high purity. And with SEC, we also see that the protein aggregation does not appear to be a significant factor because the percent main peak, which is the monomer, is essentially just a few percent difference across all formulations and all conditions, which suggests that perhaps the protein stability may not necessarily be the main factor that we're seeing affect the stability of the different formulations. So the sort of scientific conclusions of this demonstration for case study 2 are, first, that the turbidity is significantly increased in all formulations after heating. There are significant changes in the color observed, especially in the histidine-containing formulations. The DLS results show that small particles are being formed in low pH formulations largely. And we see that from 2 different HPLC methods, the formulation of the stability of the formulations does not appear to be correlated with the stability of the proteins. So from an automation standpoint, what we can see here is when we look at the overall study, from my previous experience, this is about 4 to 6 times more efficient than manual procedures or even procedures that are largely manual with some liquid handling capabilities. For this second case study, approximately 28 hours of attended labor for one scientist were needed to perform all 4 points. But this does not necessarily include the stock and mobile phase preparation, nor does it include the time it took to perform some of the stressing. The formulation itself takes about 6 to 9 hours for almost 200 formulations. And of that, only about 2 to 3 hours are really necessary to be attended labor for a scientist. And the important part here to note is that much of the tedious and physically strenuous work is actually performed by the automation. The preparation and analysis time for this entire study, including the notebooking and the report generation for all analytics, takes about 8 to 10 minutes per formulation. So when we work that out, it's about 6 to 8 hours for 48 formulations. This does not include the acquisition times for UV, DLS, or HPLC, but in essence what this is saying is that in one day a T0 can be a T0 data point or testing point can be fully performed or initiated, and that is certainly high efficiency. The advantages of the formulation, or the advantages of automation for formulation, then start to become quite clear. So we can see that there are a large number of formulation conditions that can be screened rapidly. In one case, we can do that in 96 well plates. In another case, we're doing that in 2R vials. We have multiple different formats that we can support on our systems. So it's not we can't do 384, but we can do 96 all the way to 20 mils and vials and the methods that we have now will eliminate the subjective interpretation of assay results such as color, particles, and turbidity, and all of that information then is automatically saved into a database, which can be later reviewed and possibly reprocessed if necessary. Clearly, we can see that there are some increases in the reproducibility compared to manual studies due to the fact that we can calibrate these systems, and the systems can be used over and over again for the same studies. And the system also maintains data integrity, since once the raw data is saved, it cannot be edited. It can only be reprocessed. All of the analytical results, as we've seen before, are automatically saved into one database, and that can link all of those different results back to the original vials, so it can take into account all of the compositions and all of the processing information. So this makes it very easy to see everything that was ever done with any of those vials and any of the daughter vials or daughter plates. And the intention here really in the end is to allow for the reallocation of highly valuable scientist time for the scientists to make sound scientific decisions based on the studies, and also to understand what the studies are doing, understand the data, possibly rerun samples if necessary. But this can take away some of their the time that they would be doing otherwise relatively tedious and possibly very strenuous activities. So I want to thank you for your attention. I want to thank Dave Yamani, Steve Krause, Prasad, Steve Lambert, and Freeslate and sales marketing teams. I'm very happy to have worked with all of these people, and they've helped very greatly with these studies. And in fact, Steve Lambert was the one who performed case study 1. So special thanks to him. And then, as promised, this is the formulation table that I mentioned before. This will be available for download and as part of our webinar, so you can see the different formulations that we use across the buffers, the pHs, the different excipients, and the presence and absence of sorbic acid as a preservative, and the target concentration of the protein. So here I'd like to open it up to some questions. Looks like we do have some questions in the chat.
Great. Thanks, Russell. So have a great presentation. A lot of good work's done there. We did get quite a few questions. I will try to get through as many of them as I can in the short time we have. So Russell, there's a lot of great work that went into there, and you showed the power of the system. But one of the questions that we got was, can you give us an idea of what the skill level is that's necessary to perform an automated study like this?
Right. So, if a scientist already has an automation and analytical science background, then in an analytical chemistry background, it would make learning how to do this much easier. Then it would just be a question of learning how to use the software and the automation. So generally, advanced analytical formulation and automation skills would be required to perform a study like this. And because of that, a scientist or possibly a team of scientists would need to possess amongst them understanding of the software and the hardware, and naturally having some automation experience helps with the planning and the execution of the study. But one thing that we could recommend is that a system manager, or sometimes referred to as sort of a system guru, if you will, could set up the study, and then they can work together with other scientists who can help plan and perform certain portions of the study, and this will allow for one or two scientists to possibly help delegate these activities to other scientists. And then, of course, those who are learning can then at some point also learn how to use the system at a more advanced level.
Okay, great. Somebody asked if you could please recap the advantages of the LIA software for this workflow.
Sure. So the intention for the LIA software, especially for this workflow, is that first and foremost, the LIA software encompasses the entire system to sort of create one big analytical device, if you will. And so we're using one software program to tell all of the devices what their different actions need to be, and then once those analytical devices or liquid handling devices or whatever the devices are, they'll automatically save all of that data. And with the same suite of LIA software, we can rapidly interrogate that data, bring it up, look at it, process it, understand it, and then we can also make decisions on the fly. Let's say, or shall I say, real-time decision making. If LIA software will allow us to look at our data as it's coming online from the database, and we can enable our scientists to say, oh well, given this information, maybe we should do this and this, and it will actually allow them to make those decisions if necessary. And if the study goes perfectly, or even if it doesn't, if it goes the way it's intended, you still will get the data, and LIA will allow you to rapidly create the reports and allow the scientists to make certain types of reports that can be stipulated by their management or higher level scientists to communicate throughout the company, so they can understand what's happening with the different formulations. And it will enable them to make these real decisions about which formulations are performing better, and maybe the scientists can use the data to understand why the different formulations are performing better, and that can enable them to rapidly create another set of studies using the LIA software.
Great, thanks. You showed some slides earlier where there were multiple screens that looked like they were coming from PolyView. Was that all presented on one screen, or did you is that possible in PolyView?
So are you talking about the DLS data, for instance, or which?
When you have multiple data streams in PolyView, is it possible to show multiple windows at the same time?
Yes, so I think you're referring back to this dashboard view, and yes, the answer is you can show all of that data at the same time, and if the scientists or their managers want to look more deeply into that data, they can all of that data is linked to the database, so they can just double-click, let's say, on an HPLC trace or double-click on a gel, and then they can get a larger view of that gel or the lab chip or bioanalyzer data, so they can see very quickly what's the difference between these, and is the data good. And yeah, that makes for not just the dashboard view, but also really being able to go in and look at all the details of the data, both raw and processed.
Great. Is it possible to automate the adjustment of pH? For example, titrating with an acid until the pH reaches a certain target?
So currently we don't have a fully automated titration capability. We are working on that for some of our products, and I would say that even some of those products might be coming out in the 2014 to early 2015 time frame.
Okay. Well, thanks very much, Russell. That's all we have time for today. If there are a couple of unanswered questions, and so we will follow up privately via email with you if you submitted a question and we didn't have time to get to it. Also, as you can see on the screen, you can visit www.freeslate.com, navigate to the technical resources page and select Learning Center, and that will give you the ability to look at previously recorded webinars that have been done. Okay, so that concludes today's webinar. On behalf of Russell and myself, I thank you for attending, and we really do look forward to seeing you at future events. Have a great day.